Hey, all right. So I'll go ahead and introduce. So this week we have Dr. Jennifer Yee visiting us. She got her PhD at Ohio State University, after which she started a Sagan Fellowship at the CFA, and then stayed on at the Smithsonian Astrophysical Observatory there as a astrophysicist, and she is the Deputy Science PI of the KMTNet project, as well as part of the Roman project infrastructure team.
Yeah, worst acronym ever, PIT.
That's right. An expert in all things microlensing, especially for planet searches, so happy to hear about what she's also today. Thank you.
Okay, well, thank you very much, and thank you for being here. So I work on planets, and there's a lot of ways that we can learn about planets. And every different technique has its own sort of corner of parameter space. And so in this talk, I'm going to be talking a lot about mass, right? If we compare microlensing planets to planets from radial velocity, in radial velocity, we're measuring your fundamental observable is a mass ratio, but it's basically trivial to turn that mass ratio between your secondary and your primary into an actual mass of your planet, because you just see the star and then figure out its mass. We also have transiting planets, and transiting planets, you're measuring a radius. And we can, if you want a mass for those transiting planets, then you need either radial velocity or you need to use some sort of mass radius relationship or a model in order to turn the radius into a mass. And the inverse of that is also true for radial velocities. We don't get radii for the planets. For direct imaging, what we measure is we measure the flux directly from a planet, and then we use complicated models to infer the masses of those planets, and along the way, the radii as well. And then in microlensing, our fundamental observable is the mass ratio, but unlike in radial velocity, converting that mass ratio into a mass is hard because we see the lens, the host stars, but we also see a lot of other light from a lot of other things, and the host stars just become a perturbation on top of that. And so characterizing the host stars is actually much more difficult in microlensing. But what this means is that every technique has its own kind of special spot, right? And so if you look at a mass versus semi-major axis diagram of the known exoplanets, this is just focusing on radial velocity, which is the triangles, and then transiting planets, which are the squares. And the transiting planets, of course, to put them on this diagram, we had to use some sort of mass radius relationship, and the masses are all mostly kind of fake here. But even in that context, you can see the intrinsic bias of these techniques. These techniques are biased towards shorter period objects, and the minimum mass you can get with either radial velocity or transits depends on the period. So transits stop at about 1 AU because Kepler observed only long enough to get things with periods of about 1 year. And all the planets that we're getting post-Kepler are in shorter period orbits. And then radial velocities, it's just there's the semi-amplitude depends on both the mass and the semi-major axis. And so you get this envelope on the bottom, depending on how long you observe for with X amount of precision, that determines where the bottom of your detection with radial velocity is. And I've drawn these very suggestive dashed lines here, which they're drawn at 1 AU and at 30 Earth masses. And they're very suggestive, and they sort of mark off this corner in the lower right where there's a distinct lack of planets that you're detecting with radial velocity and transits. And so this space here is exactly the space that microlensing occupies, the space between 1 and about 10 AU. And that's the core of where we detect microlensing planets. And so microlensing as a technique, those detections really complement what we get from the more prolific radial velocity and transiting methods. So what is microlensing? In microlensing, let's say we're looking at a star. All right, the star is the source star, it's gonna be in the bulge. The top picture here is a face-on view of the system as it's projected on the sky, so you're looking at it. And normally the source star is just sitting there being a star and it's not doing very much, so its measured brightness as a function of time, the magnitude is constant. And so this dotted line here just indicates the baseline magnitude of the source star, doing not too much. And then the axis down here is in time, it's in days. Now let's suppose that we put a star between us and the source star somewhere. This is gonna be the lens star. It's just some other star. And what that lens star does is it splits the light from the source star into two separate images, which are shown in magenta here. And the total area of those images is larger than the area of the source star, which means that you measure a slight increase in the flux, shown in the bottom panel, from this lensing effect. And in this diagram, I've also drawn a dashed line, a dashed circle, to show the Einstein ring. And the radius of the Einstein ring is the fundamental scale of microlensing. Everything gets measured relative to the Einstein ring. So you can see, when they've set this up, is the lens star is 1 Einstein radius away from the source star. And those are the units of the top axis, an Einstein radii. And so the Einstein ring, it depends on the mass of the lens star, the distance to the lens star, and also the distance to the source star. And you can measure it either as an angular radius on the sky or as a physical radius in either the observer, the lens, or the source plane. And for the sake of argument, we're going to talk about it in terms of the lens plane because that's what's relevant for planet detections. And so most stars in the galaxy are M dwarfs. And then the sources are in the bulge, so that makes them at 8 kiloparsecs. And then you want your lens stars in between here and the bulge, so we put them at 4 or 6 kiloparsecs. And if you put those numbers into this equation, you find out that the typical Einstein radius is 0.5 milliarsecond. And the Einstein radius is about 1 to 3 AU, which is right in that box of where microlensing detects planets, right? That's why it complements radio velocity in transit and planet detections. And so we have these things. We have our source, our lens, we've got our images, we've got our measured brightness as a function of time. We're gonna stick a planet now around this lens star. And then we have an inset on the right showing just the area around the planet, the immediate vicinity of the planet. And right now it's just the planet in that box because the planet is relatively far away from both the source and the images, especially considering that the planet is much smaller than the lens star. And then this dashed line here is going to show the motion of the lens system. And so as the lens moves closer to the source star, you get an increase in brightness as the images grow. And then maybe we take some data on this, and then your light curve is no longer perfectly pretty. It has some scatter to it. And then you get the peak brightness of the microlensing event occurs at the minimum impact parameter between the lens and the source star. And then as the lens moves away from the source, the event starts to get fainter. But you can see in the inset there that at this time, the image is starting to approach the location of the planet. And when the image interacts with the planet adds an additional magnification effect, which can get you this big signal from the planet as it distorts this image of the source, and that signal allows you to detect the presence of the planet. And as the whole system moves away, the image moves away from the planet, the lens star moves away from the source, the whole thing goes back to the baseline. And so from this picture, you can see that the key element for planet detection is that the image has to pass very near or over the position of the planet. And the images are largest, closest to the Einstein ring, and so they're most easily perturbed there. So you're most likely to detect planets near the Einstein ring, which is sort of 1 to 3 AU, which is how you get this beautiful detection space between 1 and 10 AU-ish. And that's where we're detecting all of our planets, is around this few AU region. The second thing from this diagram is that if you look at the bottom panel, there's two elements, two components to a microlensing light curve. One is the large stellar signal, and then there's a cyan box here for the planetary signal. And so in order to detect microlensing events and detect planets, you're operating at two very different timescales. So the stellar event lasts for tens of days, a couple of months. But the planetary signals that you're trying to characterize are lasting a few days or less. And so you need to observe these stars very frequently for long periods of time in order to properly characterize these signals. And that's where KMTNet comes in. So I work with the Korea Microlensing Telescope Network. And the key element of this network that makes it different from any previous surveys is that they have 3 telescopes. There's one in South Africa, one in Australia, and one in Chile. And the result of that is that you can get continuous observations of the bulge. And those continuous observations allow you to really find and characterize planetary signals. In addition to having 3 sites, they also have a really big camera. The camera has 4 chips, and it works out to be about 2.2 degrees on a side, so almost 5 square degrees collecting area. And this inset here just shows a tiny section of one of the CCDs, showing just how many stars there are in this field. And that's important because even though there's a lot of stars here, to see a microlensing event, you need the 2 stars, just completely unrelated, closer to each other than an Einstein radius, closer than half a milliarc second. So even though there's like a lot of stars per arc second here, there aren't a lot of stars per milliarc second. And so in this image, you have millions of stars, but maybe only a handful of microlensing events. And so KMTNet is observing 100 square degrees of the bulge every night, at least several times per night, but in some cases several times per hour. And so there's a tiered observing strategy set by the colors here, indicated by the colors. And the orange things have a 5-hour field. The blue ones are observed every 2.5 hours, the green ones every hour, and the purple ones are effectively every 15 minutes. So there's 2 pointings, each a half an hour apart, and they're just slightly offset to fill in the gaps between the CCDs. Because it turns out these 3 purple fields, 6, I don't know, I think of it as 3 purple fields, they contain about half of the microlensing events from this whole field, just because that's where the stellar density is highest. And the tiered observing strategy, though, is important because the cadence roughly corresponds to the smallest planets you can find. So to really find super Earths reliably and consistently in your data, you want to be observing them with a cadence of 15 minutes or faster. So 4 observations an hour. And so the work I'm going to be presenting today is primarily work from the Korea Microlensing Telescope Network. And it's not just me. There's a huge team of people who have contributed to this work. And so in addition to the science team who are shown in top here, there's also a whole operations team of people who make sure the telescopes run, make sure the data gets transferred and reduced, who take the observations. And so there's just a huge team of people behind all of these results. So KMTNet has been operating since 2015 and has been very successful at finding planets. Successful enough that I can use a real event as my example. It's my cartoon example. And so the top panel here, you can see the full stellar light curve with the planet perturbation. And then in the bottom panel, you can see an inset just showing the planet perturbation and how much structure there is in that perturbation. It's lasting for about 3.5, 4 days. And that long duration indicates it's a very massive planet. And so from this structure, we can reconstruct very well the relative properties of this planet. So the mass ratio Q, the mass of the planet divided by the mass of the host star, is 10 to the minus 3.3. So it's Jovian-ish. And then the separation, it's 1.2 Einstein radii from its star. So that's telling you, like, where was the image when this planet happened. And then you do the messy thing, which is you do a Bayesian analysis, and basically all stars are M dwarfs, and then they're all kind of at 6 kiloparsecs, because that's where you maximize between here and the bulbs in terms of detectability and all that. And then you can convert these things from the top into a 40 Earth mass planet at 2.2 AU. And KMTNet, this strategy of having multiple sites has really paid off, especially for getting the smallest mass ratio planets, so things below 10 to the minus 4. And so, like, for reference, Neptune to the sun is like minus 4.3-ish. So things in the Neptune class and smaller. What you can see here are 2 examples of other planets from KMTNet. These ones have shorter durations than the previous ones, indicating that they're smaller planets. So there's 0.75 days and then 1.5 days. The other things about these is that they have very different forms than the previous planet and from each other. And there's a bunch of different models that potentially explain them. And so this one on the left is basically a small bump. And this one on the right, though, is a dip. And in this case, you get a demagnification. You lose light because instead of enhancing the image, what the presence of the planet does is it disrupts the image and destroys it. And so you can get all kinds of different planetary signals in microlensing. And then with KMTNet, oh, this is my favorite one for showing this. There's like this little tiny perturbation at the very peak of this event. And you can really see how having the multiple sites is important, because this perturbation is only lasting 6 hours, but its observing window is split between Chile and Australia. And so you get 1 point on the rising side from Chile and then the falling side from Australia. And so with KMTNet, that's what's enabling us to find these shorter duration timescale or shorter duration perturbations, which allows us to find these smaller planets. This one is smaller than Neptune. And so to understand the real impact of this project, you need to understand where we were before KMTNet. So prior to KMTNet, in 2014, there were 30 known microlensing planets. And this is the log of their mass ratio. They're sort of evenly distributed, but there are only 3, 4 planets smaller than 10 to the minus 4. We're only barely reaching into the Neptune regime. All of these are really giant planets, gas giants like Saturn and Jupiter. And then KMTNet got commissioned in 2015. We didn't publish anything in 2015. But we started our publications in 2016. And so what this whole plot is going to be, it's going to be a histogram. The upper left-hand corner is our current year. And then the number, the plus number, is the number of planets that are getting published that year. So in this case, 2. And then on the right is the total number of planets for KMTNet, which is 2. And then in the legend, we're going to have color coding by which year the data were taken. And so in 2016, we published 2 planets from the 2015 observations, and that's from the commissioning year. In 2017, we get 4 more planets. Those are from the previous year, from 2016. In 2018, we get 13 planets, and they're distributed between these various seasons as we find and discover more signals in our data. In 2019, we catch up to all the previous known detections. And there's 30 total KMTNet planets from a variety of years. And there's 2020. 2020 was 2020. It was rough for a lot of reasons. But one thing that happened in 2020 that was very important for our project is that Wei-Cheng Zhang, who at the time was a PhD student at Tsinghua University, he developed an algorithm called Anomaly Finder to automatically detect planetary signals in KMTNet data. And so the output of his Anomaly Finder, one of the output panels is shown in the left. At the top, you have the full light curve. In the bottom, you have residuals to just fitting a star, a single star model to it. And then what he did was he fit a microlensing light curve to those residuals. And the fudge is that you allow the microlensing light curve to either be positive or negative. And from that, he's able to find all of these additional signals in the KMTNet data that were being overlooked in by-eye searches. And it's basically a miracle that this works because, as you saw in the previous examples, the structures of those planet perturbations are quite complicated. They're actually not well described by this simple microlensing model, and yet it worked. And so I'm not gonna, it worked, and so that's really, it's been a really big difference for the project. And so because of this because of this algorithm for searching for planets, we've been able to do a systematic analysis of the existing data to make sure we get all the planets, yep.
So how do you distinguish this from just probability of a star?
So
the signal is not so clear.
right. So in detail, variability of the stars have certain forms and microlensing signals have different forms. And so just the shape of the perturbations are different. Also, variability in stars tends to repeat or occur multiple times, whereas a microlensing signal will be a one-time event. So, for example, in this case, the perturbation kind of goes like this, and then it has kind of this double thing. And so it rises pretty slowly, and that's pretty different from other short timescale signals. So other short timescale signals from stars tend to be things like flares, and flares tend to rise very quickly and then decay slowly, instead of having this more symmetric kind of shape. So it's just the details of it. And so, oh, right, one of the people who's been working on this project is Ingu Shin, who's a postdoc at CFA, who's been working with me. And he's just been working through all of these candidates and analyzing them, just large numbers of planet candidates. And they're no longer the very good ones, they're all the weird ones. And the small perturbations, the partial perturbations, and putting together this complete sample of KMT planets. And you can see that effect in the publication. So in 2020, we're publishing about 20 planets per year at that point. 2021, we also get another 20 planets, but then in 2022, we get this huge jump of 48 planets because of this anomaly finder system. And in 2023 and 2024, we keep pushing, and we've just really increased the number of planets that we're detecting each year. So there's probably about 30 planets in each year's data, but because we got a big jump in 2022 because we were also picking up things from previous years that had been missed. And most importantly, the impact of the anomaly finder has been seen in the very smallest planets. We're detecting many more small planets because of the anomaly finder and because it's just helping us to pick up these shorter duration perturbations. Yeah?
Sorry, are all these stars simple stars? Or are they binaries too?
Yes. So many of them are single stars, and there are also some binaries. We get both, and we get planets around binaries.
And how is what do you learn about the statistics of planets around binaries compared with around single stars?
So far, that is hard, and so we take out all of the planets, or if it's a planet around a binary star, we're not counting it in our statistical analysis. We're just holding that for later. Because formation around binary stars is a different beast than around single stars.
But you haven't yet reported any just overall planet occurrence rates.
Yeah, so let's do that. The question you're getting at is, where are these planets fitting? What do we figure out about them, right? So our radial velocity and transiting planets are here. And then this is all microlensing planets, the majority of which at this point are from KMTNet. KMTNet has 182 of the over 200 microlensing planets. And you can see it's really filling in this region beyond 1 AU. And another effect you see here is that there's a color gradient. These points are color-coded by host star mass. And the planets are found near the Einstein radius. The Einstein radius is proportional to the square root of the host star mass, so the planets that are farther away tend to have the more massive hosts. And so you see that effect here. And then your question, occurrence rate, because so you found planets, right? And so that's what we've been working on recently. So we started by taking the complete samples of planets from the 2018 and 2019 KMT-net seasons, because those were the ones that got done first. And then for the smaller planets, there weren't a lot of small planets. So to boost the statistics down there, we used also 2016 and 2017 data in our sample. And so then you have the raw detections of the planets that we observe in a histogram form. Just, we did the statistics in a cumulative distribution, and we put the error bars on the models like you're supposed to. It's just, this got submitted to science, and for public consumption, histograms. And so we ran a sensitivity analysis on the full sample by injecting and recovering signals in the KMT-net data. And basically you find smaller planets are harder to find, and so each one actually represents a larger intrinsic population. And then you get this dark blue histogram when it's been corrected for the sensitivity.
I don't understand why the bin widths are different.
That is because there are twice as many seasons of data down here as there are up here. Yeah, so this one's twice as big, just to account for that. There are other ways you could have done that, but that's how we did it. And so we fit this with a power law, and you find smaller planets are more common than bigger planets. And you get a power law slope of about 0.6. And that's pretty good, it's a pretty good fit. But when you look in detail, and you look actually at the number of planets predicted per bin for the power law, you find that it doesn't fit the data very well. So the width here is just the width of a bin, and then the black points are, give it a power law distribution of planets, combine it with our sensitivity function, this is the number of planets I would predict, and then I give it Poisson statistics. And you can compare that to what's actually observed in each of those bins. So stuck the error bars on the model now instead of the data. And it doesn't fit all that great in detail. Like there's a lot of places where it's weird, especially right here, where the data are much below what you would expect for the power law prediction. And you also see that at the high mass end and the very low mass end. The power law is over predicting in those three bins relative to our observations. And so what we found was we can get a much better fit to the data if we fit it with a double quadratic, which then produces fewer planets in the end bins and also fewer planets in the middle where the two meet. And I found this very intriguing, particularly that there's this gap here, because this gap is right around sort of a Saturn mass ratio. And that's very interesting from a planet formation perspective, because in the core accretion paradigm of planet formation occurs in 3 phases. And so this is just, this has been known for a long time, but basically you have the solids build up very quickly, and that's phase 1, into a core of about 10 Earth masses. And then the whole thing kind of hangs out for a long time and grows very slowly because it's subject to hydrostatic equilibrium, and you just can't stick more gas on there. And then you get this really big jump once you get runaway gas accretion. And because you have these 3 different time scales, then you actually naturally predict sort of a pileup of objects right around here, and also a pileup of objects after you undergo runaway gas accretion. And that would naturally give you a 2-population model with a division somewhere Saturn-Neptune mass. And so it's just the fact that we see this structure in microlensing shows that as our samples increase, we're going to have the ability to constrain planet formation models and to understand that better.
Can I ask a question?
Mm-hmm.
So if you're plotting this in mass ratio,
Mhm.
this happens in the mass ratio, you presumably have some information about host star mass. So instead of mass ratio, you imply planet mass. Do you still see a difference?
So the key thing is presumably have information about host mass, and the answer to that is no.
Oh, okay, because earlier you were plotting the,
Yeah, so those were all kind of lies based on Bayesian analysis. So you do a Bayesian analysis with all the stars, and if you assume that planet occurrence is independent of host mass, then microlensing is random. Therefore, if you choose a random star, it's an M dwarf. Therefore, you infer a planet mass based on it being an M dwarf.
but still, if you have some information on the host star mass, if you have some correct information,
Yes,
this feature ought to get deeper.
right. Well, I mean, it might get deeper unless the fundamental property is actually mass ratio instead of mass.
No, for planet accretion, it's not mass ratio.
Yeah.
But
That's a
for
good point,
runaway gas
yeah.
accretion, it's
For random, it should be mass.
Yeah.
So if we could do this in mass, that would be better, which is one of the things that I think is exciting about Roman, which is that Roman will measure the masses of the hosts better than we do from the ground.
So you haven't done it for this sample.
So yeah, we haven't done it for this sample because we just don't have the information. You just put in random star model, you put in mass function and model of the galaxy, you get out M dwarf plus or minus some, you get out that it's a main sequence star and probably an M dwarf, but somewhere in there, yeah. Is there another question?
Can you see a bit how you do the sensitivity correction and whether it's just a correction of mass ratio or also the host mass, given that you mentioned earlier that the size is related to the mass. So I'm
Yeah.
not sure if the correction here is sensitive to also the mass, which you may not consider and artificially causing the bimodal that you're seeing. In other words, the bimodal is a consequence of you didn't do the sensitivity correction correctly.
Yeah, so we do the sensitivity correction in mass ratio. That's the observable.
Right.
And so we inject things in mass ratio. But I think that your point is the important point, is that it might be clearer in mass.
It'd be fun to try.
For color, yeah. I think that it's just, we don't do it because there is no information. And if it's correlated with host mass, it's not. But we don't take that into account, then it's too mushy. It's better to just Well, I mean, you can do that, right? You can just basically say, this is here, and then, what did I say?
I'm sorry.
Yeah, no, I mean, you basically do that. You just assume that your typical mass is 0.5 solar masses, and then you do the mass ratio and you get a mass out.
No, actually, there isn't a clear implication as far as I'm aware about whether mass ratio or absolute mass. Certainly you need an absolute core mass to trigger the envelope collapse. But then the amount of gas that's available to this could very well correlate with the mass of the planet.
No, because
So,
not true, it's only the engine.
what?
Okay, let's not go too far.
No, this is good though.
I believe
This is
it's a
exactly the point.
match. I believe it's a match, not a match. Anyway, go ahead, yeah.
Yeah,
And we don't notice it.
Sorry?
The point is we don't. So,
You're
Yes.
absolutely right, depending
so
on some theory.
it would be great to have some theory and then to use this as a constraint on the theory. So far, we've been talking about bound planets, but microlensing is also really good for free-floating planets, as many of you know, because Sam's been working on that a lot. And I mean, the key here is just it's proportional to the square root of the mass, and you can just make the mass smaller. It makes the Einstein radius smaller. It makes the time scale smaller, but it's the same. And so you can get free-floating planet microlensing events, and they just have very short time scales of only about a day or less than a day. And I'm showing two different examples here because you've got your theoretical case in which you have a point source as your source star, and in that case you get this signal and it looks like a regular microlensing event. But in practice, all of these sources are stars, and from the ground, in terms of free-floating planets, we're primarily looking at giant sources. And giant sources have a very large extent, and so you actually get a big effect from the size of the source and the fact that you're averaging your observed magnification over the face of that source. And that does two things. One, it makes your signal, it reduces the amplitude of your signal, which is bad. But the second thing is that this shape here is directly related to the angular radius of your source star. And so if you can say, well, the annular radius of my source star, it's a giant, therefore it's 5 microarcseconds in radius, then you can figure out what your Einstein radius is and actually have a much better constraint on the masses for these objects by measuring this finite source effect. And so when we did this for KMTNet, what we measured here is this is the log of the Einstein radius in microarcseconds. And you get a distribution for this. And the big straight part here is basically stars. Stars is a smooth continuous function. They're at a variety of distances. It's smooth. And so you get a nice smooth distribution for stars. But then you have this break here. It's just like an absence of things. And then it continues down below that region. And you get another pileup of objects that aren't part of the smooth star distribution. And those suggest a separate population of free-floating planets. And if you fit just this free-floating planet part and just focus on that lower left corner of this cumulative distribution, you can fit that with a power law. And for bound planets, we had 0.6 was our power law index. And you can see that 0.6 overpredicts the number of things in this plateau in the cumulative distribution function. So what we find is that the power law index for these free-floating planets is much steeper than what you find for bound planets. You get many more small things relative to big things. And in general, what we're doing is we're measuring them relative to the number of stars. And so this dotted line here is the power law with the index of 0.9, power law index of 0.9, so steeper. And this is the free-floating planet contribution. And in this particular paper, Gould's 2022, we compared it to the Chabrier mass function. And that's in the dashed line. And so then your total mass function for objects is the solid blue. And we also, well, we as a field, the MOA group did an independent measurement of the mass function, combining information from both the timescale distribution and the Einstein radius distribution, and they produced this measurement of the mass function. And the free-floating planet mass function is very similar, but they find many, many more brown dwarfs than you get from just a Chabrier mass function, which is interesting. And I was talking to Scott Kenyon at CFA about this, and he was like, well, you know what would be interesting? It'd be interesting to compare this to the Kirkpatrick mass function for the local solar neighborhood, because they really push to try to get all of the brown dwarfs and to push the measurement of the mass function into small things. And when you do that, you find that this overabundance of brown dwarfs in the SUNY mass function is consistent with what we see in the local solar neighborhood. And it's particularly interesting because if you add lines here at 3 and 15 Jupiter masses, which is the dashed and the dotted lines, you find that the objects in this range are actually dominated by things from the stellar mass function. And for the purposes of this talk, I'm going to say that brown dwarfs are not defined by mass, but they're defined both by being low mass and part of the stellar mass function. So you would say in here you get a small component of planets, but mostly you're getting dominated by brown dwarfs in this range. Do you have a question?
So why aren't you seeing those brown dwarfs? Why is the blue one not showing the same brown dwarf?
Because it just assumes Chabrier.
Oh.
Yeah.
But you have a whole distribution of the...
We have a whole distribution, but
You don't have to.
we just didn't fit it. We just assumed Chabrier and then measured the planets relative to it. I think the key thing about it is that what you get from SUNY and what you get from Google are basically the same in terms of free-floating planet mass function. And for the rest of the talk, I'm just going to focus on the results from SUNY because they actually fit this. And it has all the brown dwarfs, and that's cool. Okay. Oh, right, there's a lie. Okay, so there's a lie, which is that the situation that we've been discussing is the free-floating planet situation, where you have a planet transiting a source star. But actually, in microlensing, that looks exactly the same as if the planet is just on a very wide orbit around its host star. So you can have a star there as long as it's far enough away that you don't pick up the microlensing signal. And so all of the microlensing free-floating planets could actually be planets in bound orbits of 10 AU or more-ish. And it's always been like this caveat with microlensing free-floating planets. It's they don't actually have to be free-floating. But the thing that I realized that led to this whole work with Scott Kenyon is that the number of planets is finite. And it doesn't matter whether or not they're actually free-floating or bound, because it still places constraints on the whole population. You could say they're all bound, but if they are all bound, none of them are free-floating. You could also say they're all free-floating, but if you did that, you would then also say there are no planets outside 10 AU around stars. And both of those things are interesting. And so then, because I'm at the CFA, I hear a lot about ALMA disks and gaps in ALMA disks, and the D-Sharp survey by Sean Andrews. And then in the talks that we hear, people started saying, well, there's all these gaps. You know how you form a gap? You stick a planet in the gap. And so all of these gaps, you can stick a planet in each one and calculate the properties of the planet that makes this gap. And as I was thinking about that, I was asking them, well, where are these planets? And they're all, where are these gaps? And they're all like, well, they're at like 30 or 50 AU. And I realized that if that's true, then these things would probably show up as free-floating planets in the microlensing system, which means that those microlensing free-floating planets constrains this statement or this assumption that every one of these gaps has a little planet in it. And so I started talking to Scott Kenyon about it, and he started feeding me papers. And so he says, well, these guys, they did hydrodynamical simulations, and they put one planet in each ALMA gap, and this is what they find for their frequency. And so if you take the microlensing results, and you divide them into bins, and they're not nice mathematical bins, they're nice, convenient, warm, friendly, fuzzy-feeling bins. So we have the mass of the Earth, the mass of Neptune, the mass of Saturn, and the mass of Jupiter, and then 13 Jupiter masses. You can calculate the frequency of planets in each of these bins from the microlensing free-floating planet distribution just by doing integration, and you find it sharply decreasing. And then you can take the population of things from ALMA gaps from this survey and calculate how they distribute between these bins. And what you find is that there are fewer small planets than you see in the microlensing, and that's fine, that's good. Just means maybe some of the microlensing planets aren't bound, or they're bound in systems that don't have ALMA disks with gaps in them. That's cool. But once you get out here above a Saturn mass, there's too many predicted planets in the ALMA disks compared to the microlensing measurements. And if you look at different assumptions, there's also the Lodato study, which just made a simple hill radius scaling. This long one, which used that hill radius scaling with Lodato, but then added another layer distinguishing between whether you're opening a gap in the dust disk versus the gas disk. And then this Zhang 2023 paper, which is a different sample than the first one, you're just getting this consistent picture that there are a lot of predicted ALMA planets out at wide orbits, and that they exceed the microlensing measurements. And so one thing you can do is say, well, okay, not everything has an ALMA disk with a gap in it, right? Only about 30%, 35% of things have ALMA disks with a gap. And that will give you a factor of 3, but it won't quite really match the microlensing. Maybe you can fudge it, but it also requires that all of the microlensing planets here are bound to host stars. They can't be free-floating objects. An easier, I think, explanation is just ALMA gaps. There's multiple gaps per disk. You just don't want a planet in every one. You want to produce multiple gaps with one planet. And that would also solve your problem. But the point is that there's constraints on the physics that you're using to infer what's in these gaps, what's forming these gaps, based on these microlensing measurements.
There's also direct image constraints.
Yeah, that's next. So when we're talking about everything outside 10 AU, we've also got the direct imaging planets, which are diamonds here. And there are measurements from radial velocity. There's some detections out here. And so if you combine them and you ask, well, is it consistent with what you see with direct imaging? This is from Nielsen 2019, and then you have the GPIs. Is this solid line here, and this is for planets between 5 and 13 Jupiter masses, compared to the microlensing with the dotted line and the solid line. So the difference between the dotted line is this is the free-floating planet part, and this is the total constraint on such objects. And it's not consistent with the free-floating planets at all. It's sort of marginally consistent with the total number of objects you find with microlensing. But what you have to, then you realize, well, actually, when you're talking about direct imaging planets, all the planets are detected around really high mass stars. And so if you correct, okay, all the planets are detected around high mass stars, but most stars are low mass. And so if you correct for this, in microlensing, we're measuring everything. So we're measuring planets per star, all stars. And so if you correct for this and you say, well, there are no planets around stars that are around the low mass stars, from the GPIs, you get this correction factor. And then it becomes sort of marginally consistent with the microlensing thing, or with the microlensing measurement. But it's still real tight. And what that suggests to me is it suggests to me that some fraction of these imaging objects are actually brown dwarfs, and they're actually coming from the stellar mass function, the tail of the stellar mass function, rather than being planets per se. We do this, there's a bunch of studies that show this. So this is a different sample of planets, and in this case, they considered this possibility that some of their things are brown dwarfs and some of them are planets. And what you find is that the microlensing free-floating planet distribution is below the total. So it's consistent with this hypothesis that some of the objects they're detecting are actually brown dwarfs. And you can do this also compared to the radial velocity planets. And the thing is that microlensing for this sample, between like 1 and 20 Jupiter masses, it only predicts about 3 planets per 100 stars, which is at the very tail of the frequency you get from radial velocities for this sample. And you find a similar thing if you're talking about just the 5 to 13 Jupiter mass things. The microlensing predictions of the number of planets per star just right at the edge of the distribution predicted by radial velocities. And for this particular radial velocity study, the interesting thing is that they say their study covers FGK-M stars. But if you look at 10AU, they've only got about 40% completeness. And so if you say, well, actually, if your completeness is correlated with your host mass, you really need that, well, you might be able to save yourself from this intrinsic conflict. So what I did was I looked at their sample and I looked at the total duration of observations per star, for every star in the sample. And then this is the mass of the host star in the sample. And then I said, well, what is the period at 10 AU for this mass star? Because the lower mass stars, you need a complete period or the same fraction of the period to be observed in order to detect the planet. That's the assumption I made. And for the 5 planets they have at 10 AU, the minimum fraction of the period they have is 0.6 for, at least they detected a planet at least 0.6 fraction of the period at 10 AU. And you see that in this space, if you're thinking about period versus duration of observations, they're highly correlated with stellar mass. And so actually, if you look at their sample, they really aren't sampling the M dwarfs, which allows you to have a correction factor that brings their results into better alignment with the microlensing planets. But again, you have to assume that all of the higher mass microlensing planets are bound to their host star, are bound to host stars. And then Sky Canyon really likes debris disks, so we also did debris disks. And so in this Pierce study, they assume you have a debris disk and that the inner edge of this debris disk is being sculpted by a single planet. And based on that, you can get a minimum mass for the planet at a certain radius. And so the black line here is for their whole sample. That's the cumulative distribution of planet minimum masses. And then the colored lines here divide that by host star type. And so these are M dwarfs, there's only like 4 M dwarfs in their sample. But you can see they're all very similar, but the minimum mass is correlated with the host mass. And if you normalize it by the median mass, though, you find they all have about the same slope. And this slope, though, is shallower than the microlensing slope. So the microlensing slope for the free-floating planets is 1-ish, 0.9. And for bound planets, it's 0.6. And so this is much closer to the cyan line. And so the slope of the mass function that you would infer for debris disk planets is shallower than the microlensing function, which just means, that suggests that there's a bunch of smaller microlensing planets that aren't sculpting debris disks. So you just have more planets that aren't doing debris disk things, or they're just out there and they got ejected or whatever, and that's okay, as long as you don't have too many giant planets. And so we tried to calculate how many giant planets there should be. And if you assume that the debris disk planets are representative of the entire sample, so that stars without debris disks also have planets that are the same as the debris disk planets, then you get the solid points here. And they're consistent with microlensing, but again, they require that all the microlensing planets be bound. And if you assume that only debris disks, at the other extreme, only the debris disk planets represent only debris disks, and that stars that don't have debris disks also don't have planets of that type, then you get these open circles, which get you more comfortably under the microlensing results. And so this is basically consistent, except when you remember that what Pierce did was they calculate minimum mass. And so then that's interesting, because the fact that these things are so close to each other shows that the microlensing can place an upper limit on the maximum mass for these same planets. Or they can place a limit on whether this single planet hypothesis. So the interesting thing about Pierce is they calculate if you have a single planet, you get a certain mass for your predicted planet. And so this vertical line is Jupiter mass, and this dotted line is for a Saturn mass, and you find that over half of their planets are Saturn mass and above if you want to shape your disk with a single planet. But if you use multiple equal mass planets spaced every 16 Hill radii, then you can get much smaller planets. And whether or not this is consistent with the microlensing results really depends on how many of those smaller planets you need in order to shape them. So if you need, I did a calculation, and I calculate how many planets you could put at 16 Hill radii spacing between 10 and the inner edge of the disk, 10 AU and the inner edge of the disk, and you can put a lot of planets there. If you need all of them, then you're gonna be in trouble. But if you only need a few of them, then you might be okay. And so, in total, like when you consider all of this, there's just all these different ways of looking at these microlensing constraints in the context of other measurements. So from radial velocity and imaging, what we're finding is they're constraining things at 1 Jupiter mass and above, or 5 Jupiter masses and above. And for those observations to be consistent with microlensing, either some of those planets detected by radial velocity and imaging should be brown dwarfs instead of planets, or all of the microlensing free-floating planets have to be bound, and you can't have planets greater than a Jupiter mass around the smaller host stars, around M dwarfs. If you look at the debris disks, your constraints go down to a Saturn mass. And so either, again, all of these free-floating planets are actually bound in wide orbits, or only the debris disks have planets. Plus you get this constraint that you're close to the minimum mass, that either the real planets are close to the minimum mass that's being calculated, or there's more than one of them. There's multiple planets shaping these debris disks. And for the ALMA disks, you just can't put a Saturn mass planet in all the gaps that they want to put gaps in. It's not going to work. There's too many. And so combined together, I think the microlensing mass functions, we're measuring bound planet mass function explicitly between 1 and 10 AU, and there's some interesting structure starting to show up in that mass function, which has implications for planet formation theory. And beyond 10 AU, these different mass functions are also having implications for constraining all sorts of different aspects of planet populations. And for example, theory of how planets in structures in circumstellar disks made by planets. And I'll stop there. I can talk more about it. Thank you. Yeah. So with Roman does two things. Roman gets you smaller planets. And actually the way that Roman gets you smaller planets is because it gets you smaller sources. And getting smaller source stars has a side effect that it's easier to measure the light from the lens host stars, which means that you can get a better characterization of the system and actually get masses instead of just, you can get masses for bound planets and not just mass ratios. And you can try to constrain whether or not these free-floating planet candidates are actually have host stars or not. If they don't have host stars, there won't be light, but if they do have host stars, there could be light.
In terms of the total number of planets and events you'll record.
Yeah.
How does that compare?
They're similar in magnitude, like an astronomer's saying. Yeah. Within a factor of 2, they're the same number, yeah.
Yeah, so I have a question about this particular.
Yeah.
So you might have mentioned it. So with RV in transit, you do observe a large parameter space of masses as well, right? Like then together, do you observe any different masses there?
So the thing about the radial velocity planets is when you're talking about the more massive ones, they're expected to have undergone a lot of evolution. They're not really expected to have formed inside of 1 AU. And so then there becomes a question of what does that evolution do to your measured mass distribution? But you do, for example, see other structures, like in the radius distribution, there's this radius gap around like 5 Earth masses for very close-in planets. Although the physical mechanism is different. In that case, what's thought is that you have a Neptune and then you blow off the atmosphere, or you heat it until the atmosphere falls off and goes away. And so you have some population of things that are massive enough to hold on to their atmospheres when very close to the stars, and things where it's been lost and it's just the bare core left. So you do see structures, but they're not the same structure.
If there is a same, there is a different subset.
There's a,
I mean, it's
yeah,
you're
there's a-
right, they're looking at different distances, you
Yeah.
can't just connect it all.
right.
But
There's
if
not a
you
lot of
like cut it off a
science.
year, there's a bit of a dip.
Yeah.
Right?
Yeah, there's sort of, I'm just thinking like a couple of there's sort of gap around, I guess, Saturn,
Right. So that's,
separating
yeah.
sort of Neptune-ish things from giant planets.
Giant
Kind of correlates with that.
Right.
Yeah.
I mean, you definitely see the overall trend that there are more smaller things than bigger things. It's sort of parallel.
Keep it still in this.
This data is like for 100, 200-ish planets, right? This plot is for like 100, 200-ish planets, right?
There's 63 planets
Oh,
that go into this plot. Yeah.
100.
So it's just, so there's 185 total KMT-net planets, and this is just a subset of that data. Turns out it took a long time to get that through the referee process, but that's our current project, is to do like a full 8-year sample instead of 2.5 of another 2, but to get a more statistically significant result, yeah.
So does KME net seed to Roman, or do they keep going? So there's these 2 searches?
Yeah. So they get different parts of the space because of the different sources. So there's somewhat non-overlapping, but there is a lot of debate about what the future of KMT-net will be and how it will carry on and what science is interesting given what we have now. That's an important question.
And is there a lot to come out on planets around binary hosts? Or is that too difficult to analyze? Or what's the situation?
I think right now it's too difficult. So there's 6, maybe 10 planets in binary systems detected by microlensing. But you're looking at such a weird corner of parameter, like the observational effects are very severe. So if you say, well, in order to detect both components of the binary and the planet, both the second star and the planet both have to be really close to the Einstein ring. And that limits you to detecting systems in a very special configuration. And you know it's special because if you take it and you assume that it's face on, it's not actually dynamically stable. So they have to be in or out of the plane a lot. And that adds an additional component of uncertainty, which is that you don't know if you've got a binary star like this and a planet like this, or a binary star like this and a planet like this. And you are catching the system at a special time. And I think that it's going to be very difficult, but interesting, if doable, to try to reconstruct the underlying population that produces your observations, given that given a broad underlying population, you're only going to get a tiny sliver of it that can be observed.
Alright,
Thanks.
Upstairs.
go upstairs. So,
Cookies.
tea, coffee. So the projections to say thousands of planets, remember, or are the thousands coming from KN2?
The thousands are coming from the assumption of a mass function. Because you don't, like at the time that Roman was done, you didn't know what the mass function was.
So
So they took the Kazan mass function, that mass function is optimized there, and then they saturated it in Earth mass. I also think they haven't done that. Well, actually, no, I do think that that's better. So I used to really worry that a lot of their small planets were going to be detectable but uncharacterizable in terms of distinguishing between various inspection scenarios, but now I feel better about that.
I just want to clarify,
Yeah.
the free floating slope and the bound slope, which one's different? The free floating is different?
Free floating is 0.9 and bound is
0.6.
so.
But your 0.9 is a big error.
Yeah, it has smaller error bars than assuming. It's more like 1+1. I don't know, there's error
from
bars.
the finance ads.
Yeah?
So, yeah, it does have fairly large error bars, but it's pretty distinct from the 0.6. Like, it's
Yeah,
not-
but we cannot.
It's different by at least one signal.
We can be sure it's not 0.6. Okay, fair